Okay, good morning, class. Okay, today we are going to discuss chapter 3, which is convection for our subject KM30403 heat transfer. Yeah, for this chapter, we have 4 subtopics, which is the first one is forced convection, flow within circular tube. Second one, forced convection, perpendicular flow about circular tubes. Third one, forced convection along flat wall or plate. And lastly, free and or natural convection. Okay, physical mechanism of convection. Okay, I think we have discussed thoroughly about conduction in the previous chapter. So, as you can see that conduction and convection are similar in that both mechanisms require the presence of material medium. So both mechanism of heat conduction require a medium so that the heat transfer can occur. But they are different in that convection requires the presence of fluid motion. Okay, as we have discussed in previous chapter, for conduction, even though the medium is fluid, but if the fluid is stationary, we still consider it as conduction. But compared to convection, if there any movement of the fluid, so we need to consider convection heat transfer. Heat transfer through a liquid or gas can be by conduction or convection depending on the presence of bulk fluid motion. The fluid motion enhances heat transfer since it brings warmer and cooler chunks of fluid into contact, initiating higher rates of conduction at a greater number of sites in fluid. This is this figure 1, 2, 3 shows the type of convection that usually happening surrounding us lah. The first one is forced convection, where of course we install or have some fan that influence the heat to go up. Okay, we have there wind. Okay, wind here. Okay, okay. Wind right here. I need to do some adjustment here so that I can draw something lah. Okay, so here we have fan. Okay, this is what we call as forced convection. While for free convection, okay, or another word is for natural convection, the warm air will rising naturally. Okay, we move up naturally as we have discussed in previous chapter, right? Warm air or warm fluid will move upwards, while the cooler air or fluid will move downwards. And lastly, for the last figure is of course conduction, where there is no convection current. Convection is an important factor in heat transfer when involving fluid, either liquid or gas. The amount of heat transfer depends on the nature of the surface, its geometry, the nature of the fluid, its velocity over the surface, and temperature differences. Okay, this actually some of the factors that influence the heat transfer in convection. The first one is the nature of the surface, the geometry, okay, the nature of the fluids, velocity of the fluid over the surface, and of course temperature difference. So I think you already know that one of the important parameter for heat transfer is that we have a temperature difference. Simplify by assuming that a stagnant film of the fluid is immediate contact with the surface and the heat transfer through this film by conduction. So this assumption give approximate result that are satisfactory for many engineering purpose. So I think you are familiar with these two formula. Okay, for the first formula is of course we have there. Okay, oops. Okay, this is formula for conduction. Okay, while for this is for convection. K is of course the thermal conductivity. Okay, and H is coefficient of heat transfer. Heat transfer coefficient H depend on the fluid viscosity mu, fluid density rho, the thermal conductivity of the fluid K, the specific heat of the fluid Cp, the temperature difference between the surface wall and the fluid, which is T1 minus T infinity, and the fluid viscosity. So you can see that for the H, which is the heat transfer coefficient, okay, are influenced by the fluid viscosity, fluid density, thermal conductivity, and the specific heat of the fluid, where all this value can be, can be referred to a table. Okay, while for the temperature difference is of course given in the question. Okay, one of the dimensionless number that are being used in convention is the Nusselt number. Okay, it is common practice to dimensionalize the heat transfer coefficient H with the Nusselt number, where the formula for Nusselt number is Nu equal to HLC divided by K. Okay, the heat flux through the fluid layer by convection and by conduction can be expressed by again, if you could remember, is that for the small q is actually for the heat flux, so meaning that the unit is watt per meter square. Okay, so this is for convection, while for this is for conduction. Sorry. So taking the ratio, meaning that we divided those two heat flux, we get the Nusselt number, where Nusselt number is again equal to HL divided by K. The Nusselt number represents the enhancement of heat transfer through a fluid layer as a result of convection relatively to conduction across the same fluid layer, where if we get the Nusselt number equal to 1, which is, we consider it as pure conduction, meaning that there is no movement in the fluid. Okay. Okay, the second number we are going to use in convection is Prandtl number. Okay, the relative thickness of the velocity and the thermal boundary layers is best described by the dimensionless parameter Prandtl number, where it is defined as Prandtl number equal to molecular diffusivity of momentum divided by molecular diffusivity of heat, equal to V divided by alpha equal to mu Cp divided by K. Okay, the heat diffuses very quickly in liquid metal, where the Prandtl number is less than 1, and very slow in oil, where the Prandtl number is larger than 1 relative to momentum. Consequently, the thermal boundary layer is much thicker for liquid metals and much thinner for oil relative to the velocity boundary layer. I think when we talk about velocity boundary layer, okay, you have learned a lot, I think, during the subject of fluid mechanics. Okay, for a flow, a movement of the fluid, usually we have two types lah. The first one is of course laminar flow, and the second one is turbulent flow. As you can see in the figure here, okay, I'm not sure what is wrong with this pointer. Okay, laminar flow. The flow is characterized by smooth, streamlined, and highly ordered motion. So that too is actually the two characteristic of the laminar flow. While of course opposite of